This lecture will be an introduction to Python, focusing on some aspects that we will be using to help us understand these algorithms we are covering in bioinformatics. I'm going to talk about some basic tools, some data structures like strings and lists, the for loop so we can iterate through these arrays, and also how we can use files, because these will be useful in our examples to input data and output reports and so on. There is some overlap with the programming course you are taking, the Advanced Programming for Biology, but our focus here is a bit different. So we're going to use programming to help us understand the algorithms we cover. In any case, I don't think there is a problem there being an overlap, because even though some of the subject matter you already covered in this other course, I will not just assume that you already are comfortable with everything, because most of you don't have experience in programming. So we'll take things slow, and we will look at several examples and look at all the different bits without skipping anything and assuming that you already know this part. And I'm going to use today an example from biology, the problem of computing the fragments resulting from digesting DNA with the digestion enzymes. So this will be basically a problem of handling strings and processing that kind of data. So let's start with the basics. First, just a motivation for writing code. Of course, if you come into this course, you are probably already motivated into at least looking at code and algorithms. But there are several advantages in putting the computer to work for us. So if we are doing manual processing, we get the result of whatever we are computing or processing. When we program, we specify the recipe, and then this allows us to put the computer to work for us in executing the processes. So this becomes automated, unlike what we do with manual processing, but there are additional advantages. For example, with a computer program, it's much rarer to have some random errors, and the systematic errors are easier to identify and to fix. Whereas if you have a human doing all the processing, then often there are errors that you cannot reproduce, and so they are harder to fix and identify. Another important thing that we're going to take advantage of is that the code is actually a specification of everything in the procedure. Whereas if you have a human executing some procedure, unless they take special care into recording all the details, you probably end up with no record of how things were done. You just get the result and you don't know what happened. Code also has an advantage that it can be reused, unlike manual work, because you just have to do everything again. And of course, a computer is not only much faster than humans for some tasks, it also does not get tired. So there are very strong limits to what you can get with human processing that you can overcome with automation and programming. But for our particular purpose, we are going to focus on this basic idea that the code specifies everything. So basically, code will be the most detailed and the better way to express some algorithm. So if you can write the code for an algorithm, then it's certain that you understand the algorithm. And also, writing code in general is a good exercise to develop those necessary thinking skills to understand computers, how computers work, and to talk to computers. So basically, to be able to express yourself in algorithms in sufficiently specified procedures that then the computer can follow. So all of this helps then understand the kind of algorithms that we'll be covering in this course. Okay, so just to start, you already covered this in the programming course, but to recall and to review a bit this subject matter, we are going to use a lot of variables, and variables are names that the interpreter is associating to some memory region where values are stored. So everything in the computer is a sequence of bits, so you can imagine them as being switches that are on or off, or zeros and ones. And how each sequence of bit is interpreted will depend on what indications we give to the Python interpreter in this case, or in general to the context of the program that is interpreted them. So will they be represented as text? Will they be used as a number, as a sound wave or something like that? So this depends on how the sequences will be interpreted. In Python, we give these indications by some syntactic elements. For example, if you write a number with no decimal point, then the interpreter will assume that you want an integer number. If you include a decimal point, then this will be represented as a floating point number. If you add single quotes or double quotes, it will be stored as text, as a string. With square brackets, you indicate that you have a list of values. With these parentheses, you indicate that you have a tuple. They have different properties. We're going to see a bit more of this in a minute. And there are other data structures. For example, I show here a dictionary. We're going to talk more about these later on. But basically, we have these indicators that tell the interpreter what kind of object, what kind of data we have there to handle, and how it will interpret these other elements that we provide here. For our purposes, we're going to use these names, usually descriptive names, so that we know what we are storing in each variable, even though the interpreter doesn't care what we write here, as long as it's syntactically correct. But for us, it's helpful that the variable names are indicative of what we are keeping there, because it helps us understand the program we are writing. We also have operators, things like exponentiation. For example, these two star characters indicate that you have the power operation. So this is 4 raised to the power of 2. You can use some operators in different data types. For example, with strings, with text, you can use the sum to concatenate strings. So this plus this will be the concatenation of the text. You can also use comparison operators. For example, these 2 equals asks to compare the operands on both sides of the operator. Note that this is different from a single equal sign, which is what we use to assign values to variables. So if you use one equal sign in Python, this means the assignment operation. Whatever you have on the right side must be able to be evaluated by the interpreter, and the result will be stored in the name that you give in the left side, which must be a valid variable name. If you use 2 equal signs, then you are asking the interpreter if the 2 values are equal. So in this case, they are not. This returns a false value. If they are equal, 3 plus 3 and 6, then it returns a true value. In this case, this is the less than comparison. So 4 is less than 8. This is true. In is another operator that you can use to check if an element is inside something that contains several elements. So an iterable, it can be a tuple, a list, and so on. This also works with strings. You can check if some string is part of a larger string. So this in operator is also useful in those cases. You don't need to memorize all of these. We are going to look at these as they are needed during our examples, but this is just to give you an overview of the kinds of things that you can do with values, with variables, and so on. So let's see here a simple practical example. Suppose we want to compute the concentration of some mass of salt, sodium chloride, in some volume of water. So we can specify in this case, for example, the mass is 2 grams, the volume is 0.1 liter, but here we also need the molar mass so that we can compute the amount of sodium chloride. And now we can compute the concentration, which is the mass that we are adding divided by the molar mass. This is the number of moles that we have, and then we divide this by the volume, and this gives us a concentration that we can now print out. So if you use the print function, and then in parentheses you specify what you want to print, and you can give several arguments here, and the print function will print them one after the other. So we're printing the text concentration, then the value of this variable where we computed the concentration, and then an uppercase M for the units. So if you write this in a file using Spider, this is what comes with Anaconda, the software I recommended for this course. I'm going to show here in yellow what you write on the editor. So you can write this on the editor and save as a Python script, in this case nacl.py, for example. You can choose whatever name you want, but you should always keep this extension .py to indicate it's a Python file. And you can then run this script pressing F5 or the play button in Spider, and you will see this appear on the console. So throughout these slides, I will represent in gray what you have on the console, and in the yellow what you have on the text editor where you write the scripts. Okay, so let's look a bit more at these strings. Everything in Python, all these values that we are using are not just dead data, they are objects. And objects are basically small self-contained programs that have utilities, have methods, inner functions that you can use to do things with the data. So if you create a variable with a string, for example, Python, you need to indicate that this is to be stored as text. So you need to put in these quote marks before and after. You can use single quotes or you can use double quotes. So this is also correct, double quotes. But if you don't use quotes, you have a problem because the interpreter will try to figure out what this word means. Is it a function? Is it another variable? Something like that. And since this does not exist, it will give you an error. And even if it exists, it will probably give you something that you don't want. So remember, if you want to specify that this is text, use either the single or double quotes surrounding the text so that the interpreter knows this is just to be stored as a sequence of characters. But now this variable is referring to an object of type string that contains this data, but also contains methods that you can use to manipulate the data. For example, if you call the upper method, you need to include these parentheses at the end, which is an indication for Python to execute the method, not just a reference to the method. Then what this will do is to look at the string that you have stored inside the variable and return a copy of the string but convert it to uppercase. You can also replace elements of the string, for example, replace age with 3 dashes. This will look at the string and all occurrences of age will be replaced by 3 dashes in a copy of the string. So note that this is not changing the string you have there, it's just returning something derived from that string by applying this replace method. You can find the positions of elements. For example, O is on the index 4 of the string. This is because in Python indexes start at 0, so this is 0, 1, 2, 3, 4. And so this tells you where you can find the O. You can split. Splitting it returns a list of substrings breaking on where this sequence is found. So it finds the TH there, and it will return what comes before the TH, the PY, and what comes after there. So you have different methods that can help you manipulate the data that you have in this variable, and this is general in Python. You don't have just the data itself, you have these objects that can help you do things with the data. So let's see a simple example here. We have this enzyme. This is a type 2 enzyme that cuts DNA at these recognition sites, so TGT, ACA, and it cuts between the first T and the G, so on this spot here. And now we can simulate the digestion of some DNA sequence, for example, this sequence here, using this enzyme. I just did here this because if I put everything together, then I don't have room enough on the slides. And so I did this little trick, which is to concatenate two strings, this one and the first one. And this backslash here just tells the interpreter to pretend that the following line is in the same line as this one. So this will makes it interpret the operation as something like this. Now the reason for doing this in the slide is just so it doesn't get out of the screen, but this is the equivalent of doing something like this. So you can do it this way on the editor if you want. But what we have here is that in this variable we have the complete sequence that we want to digest. In this variable we have a specification of the recognition site for the enzyme, and now we can use the split method on the sequence to break it down wherever we find the site. So you can see that we have this site, for example, here, and so when we split we get this first fragment up to the position of the site in this first fragment here. Then we get the second fragment, the third fragment. In this case it's only 3 fragments because the site only appears twice. There is, however, a problem with this, is that we are deleting the recognition site because of the way split works. We get this first part here and go all the way to this C, and then we continue there from the TC and so on, but we lost this part here that corresponds to the recognition site. So we can solve this easily by doing 2 steps here in processing. We create a new sequence that replaces all the occurrences of the site with the same nucleotide sequence, but with a dash indicating where the enzyme will cut. So basically we get a new version of this sequence which contains, in the positions where there will be a cut, it contains a dash line like this. And then we cut on the dash line. So this throws away, it removes the dash line, but that's okay because we don't want the dash. And we get the complete sequence now without losing anything. So this actually tells us where it's going to cut and cuts on the correct spot and so forth. So you can see here, we retain this last T because it corresponds to the T before the cut, and then we get the remainder of the recognition site on the second part here of the sequence, of the digested fragments. Okay, so this is an example, a simple example of how we can use these Python methods to help us process the string, and also an example of how we can reason about these algorithms using the data structures and the methods that we have available in order to find the correct sequence of operation that gives us the desired results. Now we can look at the different fragments, for example, and ask for the length of each of them. The length is the number of characters in the string, and we can access the 3 elements of this list by the index. So the length of the first element on the list of fragments is 24. This means that we have 24 characters here on this first element. The second one is 32, so this one has 32 symbols, and so on. Okay, so now let's think of an example that is a bit more realistic, but using the same kind of approach. Suppose we have a file with a list of sequences, so each line of our text file contains 1 identifier, then a colon, and then the sequence corresponding to that identifier. Then in the second line we have another sequence, another, and so on. Now suppose that we have this enzyme, ALU1, and we want to see where it cuts, how many fragments it's going to generate for each of these sequences. So basically we want to know the identifier and each of the number or the corresponding number of fragments for each of these sequences. So in order to do this, we're going to need a few other things. We're going to need to read this file. We're going to need to loop through all of these fragments and so on. So I'm going to make a side note here, a small detour, where we're going to look at these basic pieces before we start thinking about the algorithm and how to implement it. So let's take a look at these lists, which and there are some common aspects with strings and tuples. So basically, all these ordered arrays of elements that you can access by their index and that you can slice and so on. So in the case of a list, you can create one by using square brackets and commas to separate the elements. In the case of a string, you can create a string either with single or double quotes at the beginning and the end, or you can create strings using 3 delimiters at the beginning and 3 at the end, as long as they are the same delimiters, and this allows you to break the lines, so create strings with several lines if you want to use strings with several lines of characters. In all of these cases, these ordered arrays of elements, the elements can be accessed by their index. So if you have a variable with a list or a string or a tuple also, you can access each element by indicating the name of the variable, opening square brackets, an integer with the index of the element that you want, and then closing square brackets. Note that indexes start at 0, so if you have this string, for example, the uppercase P there will have index 0, the Y has index 1, and so on. You can also use negative indexes counting from the end. So the last element has index -1, the one before that -2, and so forth. So this is how you can access a single element inside one of these arrays. It doesn't matter if it's a list, a string, or a tuple. They are all ordered arrays, so you can access individual elements in this way. You can also obtain sub-arrays by slicing the main array. And the syntax for this is after the variable name, you also have the square brackets, open and close, but inside you can specify, separated by colons, the first cut point, the last one, and the step in which you want the elements. So if step is 1, you want if step is 1, you want all of them. If step is 2, you skip 1, so you go 2 by 2. If step is 3, you go 3 by 3, and so forth. So one thing to remember is that the slice points fall before the elements, or between the elements. In this case, if you're going here from the beginning, you have slice 0 falling before element 0, slice 1 between element 0 and element 1, and so forth. This is the best way of imagining the slice, positions, cutting points, when you are thinking about extracting elements from one of these arrays. So here are some examples. If we have this list of years, then years 0 will be the first element, the 1999 there. Years from the first slicing point to the end will be these 2 elements, because from slicing point 1 to the end will be these 2 elements, because slice point 0 is before 1999, and then you have the slice point 1 here between the first 2 elements. So if you cut from this all the way to the end, and this you can do by not specifying the end or the step. So if you don't specify the end, it will be assumed to be the end of the array, and if you don't specify the step, it's assumed to be 1. So this will give you all the elements all the way to the end. Years -1 gives you the last element here, and if you do, for example, I want the list years from the beginning to the end. I'm not specifying the first 2 slice points, the first and the last, and I only specify the step as -1. So with a negative step, the order becomes reversed, and so you get the result of this will be a copy of the list with the order reversed. Here, this is an example of jumping 2 by 2. So you start with the first one, skip this second one, go to the third one, and so on. If there were more elements, you would have more like that. And other examples here. So in this case, going all the way to slice point 2, this means it's leaving out all the elements after this one. Now, one difference between lists and strings and also tuples is that strings and tuples cannot be changed. Lists, you can change what they contain. So, for example, if I say that the element of index 1 of years is going to be assigned a 0, then this 2000 will become a 0. I can change what is inside the list. I cannot do that with the string. So if I have this string Python and I say that element of index 1 will be assigned an X, this gives me an error. I cannot change things inside the string. I can create a new string. For example, I can use the first character of name, then add an X, and then use the rest of the name. And I can even replace what I have on my variable. So in this case, I tell the interpreter to compute this, then throw away what I have on this variable and replace it with the result of this operation. So I can throw away a string and replace it with something else, and that would work, but I cannot change inside the string itself. So I cannot change the contents of that object. I can just create a new object and put my variable pointing to that new object. Another thing that sometimes is useful is to unpack any iterable, any of these arrays, into different variables. For example, I have these 3 values here on a list, and I can unpack them into 3 different variables here. So the first one goes into A, the second one to B, the third one to C. You can only do this if you have a matching number of variables and values in your array. So if I try to unpack an array of 3 values into 2 variables, it will give me an error because Python will not be able to do this. And the same thing works also in strings. Just remember that the elements of strings are the individual characters. So I can unpack a string into different variables. Another thing that we're going to need is to loop through elements of a list or any of these arrays. We saw this in some of the algorithms previously, where we write something like for each element in the array, something like that. Python has a specific syntax for that, which is for a variable, a name of a variable, in the name of the array or the array itself that you want to iterate. And what this does is it's going to make this name here, this variable, point to each of the elements in turn and in order. So it's going to start by pointing at 3, and then it's going to point at 5 on the next iteration, then 7, and so forth. And what it does at each iteration is whatever we put here inside the indentation. Note this syntax here, starting with a colon and then having an indented block. This is what tells the interpreter that whatever is inside this block, this indentation, belongs inside the loop here. So this would be an example of the algorithm for adding all the elements in the array. We saw this simple algorithm last week, and you can start with a total at 0, and then for each value in the array, you compute the sum of the current value and the total so far, and you store that back inside the total. So the total keeps increasing until after you reach the end of the loop, the total has the sum of all the elements in the array. Another thing that we'll often do is to use this range constructor here. So this returns an iterable that can loop through integers, as many integers as we specify here, and starting at 0. So if you do a loop for by looping x in range 5, this will give you 5 integers, which are 0, 1, 2, 3, and 4. This is most often used to iterate the indexes of an array, because if you put here as an argument for range the length of the array, the number of elements in the array, then the variable here in your for loop will go through all the valid indexes of elements in this array, which start at 0 and stop 1 before reaching the actual length. Because if the array has 5 elements, then the index of the last element will be 4. So this is something that we will often use whenever we want to look at the indexes of the arrays. Now, another thing that is not really an important part of algorithms themselves, so this is basically just a pre-processing or post-processing part where we either input the results or write something, but for our purposes, to help us understand what's going on, it will often be useful for you to be able to read data in order to test your implementations, or to write reports in order to check if everything is going fine. So we're also going to need file access here in Python, but fortunately this is very simple. You have this open function which returns an object that allows you to access files. What you do is you give to this function the name of the file you want to access. This is either a file in the same folder that you are working in. So when you press F5 on Spider, you move to the folder where you saved your Python script. So if you keep your data files in the same folder, then all you need is the name of the file. Otherwise, you can specify some path. For example, you can have this in a data subfolder or in some other folder, for example, going backwards, and then there is another folder called data, something like that. So you can specify the path to the file, but often it's just simpler to keep everything in the same folder and don't worry about the path. To read a file, you just need to open it in this way, call open with the file name to read the text file. And then you can use this method, the readLines method, that will return the different lines in the text file as elements in a string. So let's suppose the text file is something like this. If we were to do this here, we would get in this lines variable this list of strings. Note this special character here, /n, which indicates the line break that tells any text editor, for example, to put a line break after this line 1 before starting line 2. So these characters are actually there on the file, and they are what allows the text editors to show you the file with different lines. So we get these line break characters here also on the string, but we have everything in a list of strings, and then we can close the file. Closing the file, if you do it like this, is necessary to tell the operating system you are no longer using the file. Otherwise, people trying to edit the file or something like that would get an error. And this is what we have, the list of strings with the content of the file. Usually when we read files, we will just do it in a single line, because when you call open the name of the file, you get that object that has the readLines method, the file object. So you can just call the readLines method on the result of this operation, and you get the list of strings for the file. Since the file itself, the file object, is not assigned to any variable like we did here, then Python knows it will not be used again, and it will eventually close it and get rid of whatever memory it's taking up in your RAM. So doing like this, you leave it up to the interpreter to clean up after you read the file. So this ends up being much simpler to write as code. Basically, this will be one way to read text files, and we're going to use this regularly in our exercises because it's simpler to give you the text files with the data for you to experiment with. Okay, so let's get back to our example. We have a text file with this information, the identification of each sequence and the sequence itself, and we want the list with the count of fragments we have digesting with this particular enzyme. So what we can do is we specify these two variables. This is the recognition site for the enzyme. where it will find the place to bind. This is where it will cut in the recognition site. This is a list with all the lines here on this text file, which include the identifiers and the sequence. And now we can loop through all these lines. So let's create this for loop where we have this SL variable pointing to each of the lines in the sequence lines list there. And we're going to break each line in two parts, the identifier and the sequence. So we're going to use split with a colon here and unpack this list, which has these two elements, into the identifier and the sequence. Now we're going to replace on the sequence the recognition site of the enzyme with this string that marks the cutting point, so that then we can cut it, split it on the dash sign, and print for each of these sequences the identifier and how many fragments we have. So how many fragments will be the length of this list. If this list is length 1, we have only one fragment, there was no cut. If this list is length 2, there was one cut, we have 2 fragments, and so on. Because this list is the list of strings with the different fragments resulting from the digestion, something like this. So if this list has 3 elements, then there are 3 fragments after digestion. Okay, so this is the solution here. You see, it's not a complex algorithm, but you see these different examples that we have. These elements. We have strings, we have a list with all the lines in the file, we have a for loop to iterate through all of these lines, then we process those strings using split and replace here, and we print out the results. The results will be the identifier for each sequence, followed by the number of fragments we get after digestion. Okay, so now let's complicate things a bit and imagine that we have 2 files. We have one file with the sequences, we have another file with information about different restriction enzymes. For each one we have the identifier of the enzyme, the site it recognizes, and where in that recognition site it will cut. And we have this file with different enzymes. And we want to create text files with reports for each enzyme. So each text file will be named according to the identifier of each of the enzymes. And in each of these text files, we want this same information, the identifier and the number of fragments for each of the sequences that we have. So this is now a bit more complex because not only do we need to read these 2 files, we need to digest all the sequences with all the enzymes, and we also need to write files. So let's take a look at how we're going to write a file. It's not difficult in Python. We use the open function at the same, just like reading files, but we add an additional argument there indicating that we want to open the file in write mode. So this is just a string with a W there to indicate write mode. This will either create the file if it doesn't exist, or if the file exists, it will delete everything in the file and create an empty file. And then we can use write to write strings into the file. For example, here I open the text file and I write some text, some more text, and so on. Note how this ends up looking in the file. Since I wrote here some text and then I wrote some more text, but I did not put a line break between these 2 strings, these 2 were all glued together in the same line. Only after these characters, the line break, does the text interpreter read this as a new line, and then it changes to a new line. So if you are writing text to a file and you need to break lines, create new lines, add these special characters into the string. When you have these line break characters, the Python interpreter will convert this into the appropriate line break code for your operating system. For example, in Linux it will be byte 10, in Windows is a combination of 13 and 10, I think in Mac it's the other way around, something like that. These are historical conventions. But if you use this /n, the \n, you'll have the correct line break sequence for your operating system, because the interpreter takes care of that. Just remember to add this everywhere where you want to break a line. Otherwise, you will not have the correct line breaks. After you write everything, you close the file. This is important because it not only releases the file so that others can use them, but it also tells the operating system to write everything, because usually for optimization, everything you write will be stored in memory and just written at once when you close the file. So it may happen, if you forget to close the file, that the file is empty after you think you wrote everything there. So let's see how we can process sequences with several enzymes. We will read these lines for all the sequences. We will read the text with all the enzymes, so use read lines on both of them, and we get two lists, a list of lines from the sequences text file and a list of lines from the enzymes text file. And now we can nest two for loops. So for each line in the enzymes file, we are going to create these variables, the identifier, the recognition site, and the specification of the cut point, by splitting the line with the enzyme information using a semicolon, which is the character that is separating these elements. And so we have these in three variables. Remember that this will be a list of three elements, and we are unpacking the list into the variables. And now we're going to create a list of strings with all the different counts that we have. And so we will do this for each sequence. We're going to do the same thing, split and unpack the sequence and the identifier. We're going to do what we did before, mark the cutting point, replace, and then use the split to get the fragments. And we're going to append to this list, where we are counting everything, a string with the identifier, a tab character. This is useful when you want to create two columns always at the same distance, and the length of the fragment list that we have. So this will be the number of fragments in this case. Of course, since we are creating a list of strings here on the counts to export to the text file, we need to convert this number, which is the number of elements in the list of fragments, into a string before we can concatenate it with these other strings. But this you can do with this function, str, which converts any other kind of object into a string. Then we add the new line character, so that when we write the files, we have a line break at the end of each of these lines. Now for each of the enzymes, we open a file with the name corresponding to the enzyme identifier. We write all of these strings into the files. So you can do this by using write lines. This is analogous to read lines, but while read lines reads all the lines into a list, write lines writes all the strings of a list into the file. And then we close the file. So note the indentation here. This block is done for each sequence. This whole thing is done for each enzyme. And so we are creating a file for each enzyme where we write all the counts for all the digestions. Now, one problem is that this code is very messy. We are mixing together lots of different things, reading the files, doing nested loops, going through the enzymes and the sequences, and then writing the sequence files, and everything in a monolithic block that we cannot really test appropriately. We cannot reuse parts of the code. And if you start writing code like this, then as things get complicated, the code becomes completely unmanageable and we cannot even understand what we're doing. So this is another thing that you already covered, functions, and it's a basic element of Python that will be very important for us too. The idea here is that if we write a script like we did, mixing everything together. If we want to do something else with it, we'll probably have to rewrite the code. We cannot test it in parts, cannot reuse parts of the code in other programs, or even change things like adapting to different files or something like that. We will have to change everything about the code. But especially as things get complicated, then the script becomes harder and harder to understand if we do it like this without proper structure. So we're going to use functions to solve this problem. You already covered this, but just to recall, we create a function in Python with this keyword def and indicating the name of the function and the parameters, which are the local variables where the function will receive elements. And one important thing is that the function isolates all of these local variables. So all of these a, b, result, and so on that we have in this function to compute the sum of two elements will belong just inside the function and do not interfere with anything outside the function. So you can use the function like this, calling the name of the function and then inside parentheses the arguments that you want to supply into the parameters. Note that the arguments must be something Python can evaluate at the time you're calling the function, because it needs to provide those values to the function. But the parameters of the function are local variables where the arguments will be stored when the function executes. So another important aspect here of the function is that the function is a general recipe. When we write the function, we don't care what a and b are, they can be anything. We just specify the general operations of adding these two numbers and returning the result. When we want to add some specific numbers, then we provide arguments with the actual values of the numbers we want to add. So this allows us to create these general recipes that we can use to break down our problem into simpler elements, and these elements will be isolated from the rest. So we can be sure that as long as they work well, we can then fit them together in any way that we like to get our final results. So this is illustrated in this case. If I add 3 plus 5, I created an a variable here with 3, a b variable with 5, but these variables a and b only belong to the function. Also, result, another variable that is created inside the function, only exists inside the function. So if I try to use to see what a has or result has here outside the function after I called it, I cannot see it because there is no, Python doesn't have that name outside the function. So these are the important features. We can isolate the execution of the code, and this allows us to decompose complex problems into simpler parts. And then when we want to use the function, we just call the function using the name of the function, so that object followed by parentheses. Even if we have no arguments, you need to put in the open and closing parentheses to indicate to Python that you want to execute the function. The function returns on this instruction, return. So when Python finds this instruction, it will leave the function and give to whatever called the function all the values that you put after return here. If a function does not have return, then it returns none, that empty value. So let's go back to our examples and try to decompose the problem. Instead of doing everything in the single monolithic script, we're going to break it down into different parts. We need to read the sequences file and get a list with identifier and sequence for each of the sequences in the file. We need the same thing for the enzymes. We also will create a list with the identifier, the recognition site, and the cutting point indicator. We need to have a function to cut one sequence using one enzyme and return the fragments. And then we're going to cut all the sequences in the list. So this is a general hint. If you have one thing that you need to do over and over again, that's a good way to break down the problem. Write some code to do this once, and then you call that code every time that you need it. So this would be, we have one function to cut one sequence with one enzyme, And now we're going to create a function that uses that one to cut all the sequences and then write the report for that enzyme. And finally, we create a function to write all the reports. So this would be the first step, thinking about how the algorithm breaks down, how the different pieces work together and what pieces you have. And then you can actually, if you're writing the code, you can actually write the outline of your program by just writing the signatures of your functions and these document strings for the functions. These doc strings in Python are strings that you write right after the definition line here, and they can even be accessed with the help function. So the help function looks at the doc strings of functions to help you understand how they use. But this is also useful when you're thinking about structuring a program, just to write down what you want each function to do and to think if everything will fit together. So we have this function to read the sequences. It needs the name of the file, and then it returns a list of tuples with the identifier and the sequence. This one reads the enzymes. It also needs the name of the file, and it will return a list of tuples with the information for the different enzymes. Now, to digest one sequence, we need the sequence, the recognition site for the enzyme, and where it will cut, and this will return the list of fragments that we obtain from that digestion. Then we need the report. So we need the file name for the report, the list with all the sequences, and the information for each for this particular enzyme, the recognition site and the point it will cut. So this function will then create the report file where it will list how many fragments for this enzyme we have in each sequence in this list. And finally, we have the main function here, which will write all the reports. It needs the name of the file for the sequences, the name of the file for the enzymes, and then it will do the rest. Now, this does not yet implement our code, but this way we already know which functions we're going to write. We broke down our code into different pieces, and we have an idea how things will fit together. So now we can start implementing and testing the functions, focusing only on each of them. And this will be a general approach for trying to understand any algorithm, no matter how complex it is. Break it down into simple parts, look at each part individually and how they fit together, and this will give you a good idea of the algorithm. So for this example, we have first the function to read the sequences. We already saw how to do this. But basically we're going to read all the lines in the file. We're going to iterate through the lines, and we're going to start with an empty list for storing all our sequence data. So now we're going to split each line of the file on the colon, because this separates the identifier and the sequence, and we're going to append to this list. This append method adds elements at the end of the list. We're going to append a tuple. Look here, these parentheses, that contains two things, the identifier and the sequence. Because we don't want that line break character at the end of the sequence, we can use this strip method in strings that cleans all the white space, so spaces, tabs, new lines, things like that, from the extremities of the string. And now we can test this function. So we're going to call the read sequences function on the file with the sequences, and we're going to see what we get in this list. So in this list we get a list of tuples that has the identifier and the sequence for the first sequence, for the second sequence, and so on. So this way we can check that this first function is working. This is important because if you don't check on each function if things are working, when you bring everything together, if they are not working, then you'll have a lot of extra labor in trying to figure out what went wrong. So now the same thing for reading the enzymes. The only difference is that the enzymes the information is separated by a semicolon in the text file, but the rest, the structure is similar. And now we have 3 items of data to store on each tuple: the identifier, the recognition site, and the cutting point. We also need to get rid of those line breaks here. But other than that, the structure of this function is similar, and we get here, after testing, we see the result. We get the information for all of the strings in the text file, for all of the enzymes in the text file. Now, this is just a rehash of that step we did so far, which is to replace the recognition site everywhere it occurs with that string indicating the cutting point with a dash, and then splitting the marked string with on the occurrences of the dash. And this will give us a list with the fragments, and this is what we return. So one way of testing this is to create a very simple string, for example this one, where we artificially put this recognition site TT. We specify that we want to cut between the two T's, and now we can check if we have the correct fragments there. So if you use simple examples, it's easy to check if you are getting the right answer from your function. Remember, these parts in yellow, I'm writing the code on the editor, and this will all be the same file. So I'm writing all of these functions on the same file with my code. Now, to create one report, we have this function here that receives the file name for the report, the list of all the sequences, and the recognition site and cutting point for this particular enzyme. So now what we need to do is to open the file for writing, and the name is given on this parameter here. So we receive an argument with the name of the file. And now for each line, for each record here on the list of sequences, I'm going to unpack. So each element on the list of sequences is a tuple with the identifier and the sequence. I'm going to unpack it into these two variables, and then I'm going to obtain the fragments by simulating the digestion using this fragments function. Now I'm going to write this into the file, and I'm going to use this method here from the string, which is a format method. That is very useful when you're writing information that you want to write in some particular manner. So what you do is you create a template string or a format string where inside the curly braces you specify the indexes of the arguments you're going to give to format. So this would be put the first argument here, then a tab character, then the second argument here, and then a new line character. And now I can put here as arguments in the format for that string the sequence ID and the length of the fragments I obtain, of the fragments list. This is practical because format does all the conversion necessary in order to put everything into string. So sequence ID is a string, there is no change necessary, but the length of the fragments list is an integer, and format will convert it into a string and place it here where I specified this particular argument. So this makes it easy to compose your reports as you want using this template string and the format method. So now we can test, we can create a simple set of sequences, S1, S2, S3, with just these sequences here. And we can create a test report where we use this list of tuples and we use this very elementary hypothetical enzyme to check if we get the correct results. So create report will create a text file and does not return anything, because this function is not meant to return a value. It's just meant to open the file, write everything into the file, and then close it when it's done. So it creates the file on your current working folder. To check if the file is correct, you can either open it with some text editor, or you can do something like this. So I'm going to open the file, read all the contents of the file as a string, and then print a string. And this tells me what I have inside the file, so I can check if I have the correct number of fragments for my test sequences here. Remember, test your functions with simple examples to make sure everything is working before moving on. And now finally we bring everything together. We have this final function to create all the reports. It receives the name of the sequences file and the enzymes file. it reads all the sequences and all the enzyme information into these two lists of tuples by using these functions that we created at the beginning. And now for each enzyme, it will unpack the information we have on the list into the identifier, the recognition site, and the cutting point, which is this ordering of the tuples that we are creating when we read the information from the file. And then it will call the create report function, giving as a file name the identifier of the enzyme concatenated with .txt, so we have files with the txt extension, all the sequences that we read, and the information for this particular enzyme. So after this loop ends, we have all the different files generated in our folder. So this would be an example for testing our function with this sequences txt file and this enzymes txt file. Okay, so to sum up this part, we looked at some basic Python tools that we're going to start using, and these first exercises dealing with strings, lists, tuples, and so on, so that you have the basic tools to implement some of the algorithms that we've been looking at. As we proceed along the course, we will start looking at more complex data structures, at different constructions and flow control structures here in Python and so on. But the idea will be to use Python as a tool to help us explore and understand algorithms in bioinformatics. Of course, at the same time, you will also use Python to gain some experience, some practice in thinking computationally, and in which will help understand all of these algorithms. So now today we saw strings, lists, tuples, and doing this unpacking and iterating with the for loop, and also files. Using files is just a practical tool to make it easier to work with more realistic examples, to examine the output of your algorithms, of your implementations, and so on.